For Lab 2, titled Motion of a Falling Object, I observed the motion of a crumpled paper towel falling from rest and slowly straight down. The objectives of this lab were to analyze and predict the motion of an object under non-zero net force, in this case a falling object. Also, we were to understand the motion under Newton's laws. In the case of the system observed, the net forces acting on the paper towel were due to the sum of the gravitational force from the Earth and the drag force due to air resistance on the object. Thus, it can be expected that a model of just gravity alone as the net force would overpredict the falling distance of the paper towel because by ignoring the drag force that exists, the downward net force is greater and therefore by Newton's second law the velocity would be larger. A model that includes gravity and drag would be a more accurate approximation for the paper towel's motion. The motion was analyzed in Tracker and modeled using B-idle. A comparison of the observed and computational data allowed for the observation that the system was under non-zero net force and its terminal velocity. Following a comparison of the predicted motion of the paper towel, modeled with and without drag force, as expected, the model of drag and gravity fit the observed motion of the paper towel substantially greater than that of gravity alone. Two fundamental principles were relevant to this lab: Newton's first and second law. Newton's first law of motion states that an object will move uniformly unless acted upon by external force. There is not constant velocity observed during the paper towel's motion because of the presence of the external forces of gravity and drag. Next, by Newton's second law, also known as the momentum principle, the acceleration, which is just the change in velocity over a time interval, of an object under external net forces is proportional to the size of the force. Because the net force is non-zero in this case, there's not constant velocity due to the agents in the surroundings, gravity due to the Earth, and resistance from the air. After inputting the captured motion of the paper towel in Tracker, position and time data points were extracted from the frames of its motion in the video. I lined the axes with the paper towel's motion, which was in the negative y direction. The origin was also set to the initial position of the paper towel in the video. The program output a graph of the position and time of the paper towel's motion over the 0.6 second time interval, which displayed a curved graph for a while demonstrating its acceleration. However, then its slope is constant, meaning no acceleration and constant velocity. I took the initial position, initial velocity, and final time data from Tracker and input these values into the code for both the computational model with and without the drag force included. The paper towel's mass and the value of the gravitational force were also input. Newton's second law was used to derive the velocity and position update formulas here. After running the model with the net force only, including gravity, a visual and graph of the paper towel's motion was output. This predicted motion was very different from the observed motion of the paper towel, as it overpredicted the falling distance of the paper towel. This means that the object underwent additional forces from the surroundings, which we know to be the drag force. The drag force was accounted for in the code using the turbulent drag force equation proportional to the proportionality constant b and the square of the paper towel's velocity. The value of b was determined by choosing the value that output a final position value closest to that which was experimentally observed during the paper towel's trajectory. The equivalent assignment statement for the turbulent drag force is present here. So in the code that included the drag force, the b value was input here, and the drag force equation is present here. The net force was updated to be the sum of the weight force and the drag force instead of just the weight force alone as before. When the code is run, you can see a visual of the paper towel's predicted motion, which accounts for the force due to gravity, depicted by the yellow arrow in the negative y direction, and the drag force, apparent from the blue arrow in the positive y direction. As you can see from a plot of the observed motion and the predicted motion with weight force and drag, the model including the drag force along with gravity yields a much more accurate prediction of the paper towel's actual position. So what does this mean? To check for the terminal velocity in my system's motion, I use Excel to calculate the velocities of the paper towel under only weight force and then under weight force and drag force. As seen in the graph, the terminal velocity is predicted by the model that included both weight force and drag force. Terminal velocity is reached towards the end of the paper towel's motion as the graph becomes linear, meaning the object had enough upward drag force to counteract the downward force of gravity, resulting in a net force equal to 0, and thus by Newton's second law, no change in velocity. To demonstrate how non-zero initial velocity in the negative y direction from the paper towel being thrown downward would impact the terminal velocity of the paper towel, I input an arbitrary value for the initial velocity, which was negative 15 meters per second. From running the code, velocity versus time graph is output. As you can see, throwing the paper towel down would result in a drag force which is actually slightly greater than the gravitational force on the paper towel. This results in deceleration of the paper towel. However, Eventually, terminal velocity is still reached at approximately the same time, which is about half a second, indicated by the linearity of the graph. The terminal velocity is the same at about -3 meters per second. This is because terminal velocity is only dependent on the mass, surface area of the paper towel, and the density of the medium in which it was moving. None of these parameters changed, and thus the terminal velocity remained the same. Thank you for watching.